As a product manager, the biggest mistake you can make in system design interviews is preparing for them the same way a software engineer would. Though the question itself may be the same, the evaluation criteria is completely different, and your preparation needs to be too. That's why in this video, I'll break down what system design interviews are actually testing, how to approach them using the most effective yet simple 5-step framework, and applying that same framework to a common interview question asked at top tech companies, which is to design Google Calendar. Let's get started. First off, what are system design questions? These questions ask you to design a large-scale product or feature by outlining core components, defining requirements, translating those requirements into your system, and explaining the trade-offs behind those definitions. Some examples include design Messenger, design TikTok. How would you build tiny URL? Though the actual system design question is the same for both software engineers and product managers, in a SWE system design round, the interviewer is evaluating whether you can architect and engineer a technical system that scales reliably under real-world constraints. On the other hand, in a PM system design round, the interviewer is evaluating if you can define the right system to build, prioritize the most important requirements, and evaluate trade-offs in your design. You will need technical fluency to reason design choices at a high level, but you are not expected to explain the detailed implementation of your system like a software engineer. With that being said, let's jump into the 5-step framework we can use to answer system design questions for product managers. First, we make sure we understand the product and scope down the key workflows we'll be designing. Given the scope, we'll then define the functional and non-functional requirements required for the product and use that as guidelines for the system we're designing. Next, we want to outline a high-level architecture, translating the functional requirements into a box and arrow diagram. Then we want to do a deep dive on 2 critical flows and refine the design to reflect how you'd support the non-functional requirements. And lastly, since every system design involves trade-offs, you should call out the ones you're making and explain how they still align with the product's goals. Before we dive into a solution, I wanted to make a quick disclaimer here. There are a few foundational system design concepts you'll need to know, and I'll list them on the screen here. But before you start panicking, in my next video, I'll review each one and show you how to apply them to system design questions so you can confidently apply them in your next interview. Without further ado, let's walk through how to answer Design Google Calendar to bring this framework to life. Let's start by aligning with the interviewer on what the product is, who the key users are, and their use cases. From there, you want to prioritize 2 to 3 core workflows to focus on in your design and explain why. You won't have time to cover every use case in a 45-minute interview, so it's important to prioritize the ones that matter most and explain that reasoning out loud. First, what is Google Calendar? Google Calendar is a scheduling tool that lets users create events, invite others, and receive reminders so they can organize their time. The primary users are individuals organizing their own schedules and coordinating meetings. Invited attendees are also part of the core flow, responding to events and receiving reminders to stay updated as well. The broader product also includes administrative and enterprise roles, but for this design, we're intentionally going to leave those ones out to keep the scope focused on the core scheduling experience. Now, given the 2 primary users, what are their core workflows? At a high level, the core workflows are simple. Users create and edit events, view their schedule, invite attendees, and receive reminders before meetings. We're also going to leave out workflows that aren't integral to the core scheduling experience, such as offline sync, file attachment within events, and third-party integrations like with Slack or Zoom. Now that we've defined the core workflows, the next step is to outline functional and non-functional requirements for the product. First, let's define 3 to 5 functional requirements, which are the core capabilities the system must provide for users to accomplish their goals. For Google Calendar, this would include allowing users to create, edit, and delete events, including details like the title, time, time zone, location, and notes. Next, users should be able to view their calendar in day, week, or month format and open events to see more details. Additionally, users should be able to invite other attendees, manage participants, and track responses such as accept, decline, or maybe. And lastly, users should receive reminders for meeting events that they responded yes to attending. After defining the functional requirements, you want to identify 2 to 3 non-functional requirements the system must prioritize. These describe the key traits the system needs to operate effectively in real-world conditions, such as performance, scalability, reliability, availability, consistency, and security. Here's a quick rundown on the most common non-functional requirements. First, for performance, how fast does the system respond when a user takes action? For scalability, can the system handle increasing users, traffic, and data without degrading? For reliability, does the system consistently function correctly without errors? For availability, is the system accessible and usable when users need it, even if some components fail? For consistency, is the data stored and returned by the system correct and trustworthy? And lastly, security, are only authorized users able to access or modify sensitive information, and is the system protected against abuse? To figure out which non-functional requirements to prioritize, you need to ground your thinking in scale and usage patterns. So what's the expected scale? Are there traffic spikes or hot users you need to design for? We can do some quick estimations to understand the number of users using Google Calendar. We can assume Google Calendar serves hundreds of millions of users globally, and usage is read heavy since people check their calendar far more often than they create or edit events. Let's assume 100 million active users globally, and that on an average day, a user views their calendar about 10 times and creates or edits around 3 events. That gives us roughly 1 billion reads per day and 300 million writes per day. Immediately, we know that this is a read-heavy system. Now let's think about traffic patterns. Usage isn't evenly distributed. We'll see predictable spikes in the morning when people check their schedule. We'll also see time-based bursts when reminders fire, like 10 minutes before meetings or on the hour. If even 10% of users have a reminder firing in the same minute, that's 10 million reminders triggering at the same time. There aren't traditional hot users as well. Instead, we have hot moments and hot events. Large meetings like all hands can create bursts of updates and reminder traffic all at once. With that being said, we can now prioritize the non-functional requirements that matter most to the system. For Google Calendar, data consistency is critical. With around 1 billion reads per day, even small inconsistencies can show the wrong meeting time or attendee status. In a scheduling product, incorrect data directly erodes user trust. Next, we want to prioritize availability, which means the system remains operational even when components fail, such as a database outage or a worker crash. Users should still be able to access their calendar even if part of the system is unhealthy, because scheduling is time-sensitive and interruptions can directly impact important meetings. And lastly, we have performance. This is a read-heavy system that users check repeatedly throughout the day. Responses need to be fast and reliable, especially during peak traffic, because scheduling is inherently time-sensitive. Great. Now with the functional and non-functional requirements pinpointed, we now want to start diagramming the high-level architecture. The goal here is to make sure every functional requirement is reflected in the diagram. And before we start freaking out because things are getting a little too technical, we only really need to cover these 4 things. Number 1, client and API gateway. Number 2, core backend services. Number 3, APIs. And number 4, databases. Let's start with the client or the user-facing layer where people interact with the product, such as the web and mobile apps. For Google Calendar, the web is typically used for heavier planning, like creating and editing events. Mobile is used for more quick checks and time-sensitive interactions like viewing today's schedule or receiving reminders. Both clients send requests into the system. Those requests first hit a single entry point called an API gateway. Think of this as the front door of the system. It routes traffic to the appropriate backend service depending on the user's requests and handles system-level responsibilities like authentication and rate limiting. Behind the gateway are the backend services, where each one is responsible for handling a specific function in the system. So what backend services are needed for Google Calendar? First, we have the calendar read service. This handles fetching events for a specific time range and rendering day, week, or month views. Second, we have the event write service. This handles creating, editing, and canceling events. Next, we have the attendee service, which manages adding attendees and updating RSVP states. And lastly, we have the reminder service. This service schedules and triggers notifications at the correct time. It's important to note that the reminder service runs asynchronously in the background, so when a user creates or updates an event, they receive confirmation of their changes immediately without waiting for notifications to be processed. Now that we connected the backend services to the API gateway, the gateway needs a clear way to communicate with them. That's where REST APIs come in. The gateway exposes a REST API, which is simply a structured way for clients to interact with the system. It defines a set of endpoints that map to specific actions using standard HTTP methods like get to retrieve data, post to create, put to update, and delete to remove. For Google Calendar, the backend services would expose the following endpoints. For the calendar read service, it would expose get calendar events, which retrieves a user's events so they can view their schedule. For the event write service, it would expose create event, which creates a new event and stores its details. Also update event, which modifies the details of an existing event. And lastly, delete event, which removes an event from the system. For the attendee service, it would expose get attendees, which returns a list of attendees for a specific event. Also update attendees, which manages event participants and their RSVP status. For the reminder service, it would expose get schedule reminders, which retrieves reminders that are scheduled to fire. Also create reminder, which schedules a new reminder for an event. Next, we have update reminder, which modifies the timing or settings of an existing reminder. And lastly, we have delete reminders, which cancels a scheduled reminder. So far, we've talked about how requests flow through the API gateway into backend services. But once a service processes a request, it needs somewhere to store and retrieve the data, which is where databases come in. When designing the data layer, there are 4 things that you should always clarify. First, what data is being stored? Next, how are these data entities related to each other? Next, which service reads or writes to each database? And lastly, what type of database are you using and why? For Google Calendar, we'll focus on 3 core tables: the events table, the event attendees table, and the reminder jobs table. The event table stores the core event metadata, including event ID, which is the primary key, user ID, title, start and end time, and time zone, with the following data types. This is the primary record that represents a scheduled event. The calendar read service queries it when users view their schedule. Event write service creates, updates, or deletes rows in this table. And the reminder service reads from it to retrieve event details when sending notifications. Next, we have the event attendees table, which includes the event ID, user ID, and RSVP status. This links users to events and tracks RSVP state. It creates a one-to-many relationship where one event can have many attendees. The event ID in this table is the foreign key referencing the event ID in the events table, which connects each attendee back to a specific event. The calendar read service reads from this table to display attendee information. The attendee service writes to this table when users add attendees or update their RSVP, and the reminder service reads from it to determine which users should receive notifications. And lastly, we have the reminder jobs table, which includes the reminder ID, which is the primary key, event ID, user ID, schedule time, and status. This tracks schedule notifications, including when a reminder should fire and whether it was sent successfully. The event ID in this table serves as a foreign key, referencing the event ID in the events table, linking each reminder back to its corresponding event. The event write service writes to this table when events are created or updated with reminders. The reminder service reads from this table to determine which reminders are due, processes them, sends notifications, and then updates the status to reflect whether the reminder was sent, failed, or retried. Next, we want to classify if the database is SQL versus NoSQL. At a high level, SQL databases are used when the data has strong relationships and must stay consistent across multiple tables. For example, let's say you're designing a ticket purchasing app. When someone purchases a seat, you must charge their card and reserve that exact seat together. If one succeeds and the other fails, the system is broken. You want to use NoSQL databases when you're optimizing for massive scale, flexible schemas, or extremely high throughput, and slight inconsistencies in data are acceptable. For example, let's say you're designing an observability app and you're logging millions of user activity events per second. If one log entry arrives slightly late or out of order, the product still works. For Google Calendar, events and attendees are tightly coupled, and data consistency is critical, as mentioned earlier. If the event time updates but the attendees table does not reflect it properly, users miss meetings, which affects the core scheduling product from working. This means all three tables should be SQL. Now that the high-level architecture is done, we want to do a deep dive into the architecture. The goal of the deep dive is to pick one or two key workflows and show how you improve the system to deliver the non-functional requirements we outlined earlier. This includes data consistency, availability, and performance. For Google Calendar, we'll focus on these two workflows. Number 1, creating, updating, or deleting an event, and number 2, viewing the calendar. Let's ensure that each non-functional requirement is satisfied for these key workflows. Starting off with consistency. Consistency means that the calendar always shows the right event details including time, time zone, and attendees, with no partial updates or duplicates. The main risk is that an event update succeeds, but related data such as attendee records does not, which creates inconsistent or confusing states for users. To prevent this, the event write service executes all changes for a single action within one atomic transaction, ensuring they either fully commit or fully roll back. As a result, users never see a broken or half-updated event. Next, let's move on to availability, which means the system remains operational and responsive even when components fail. The biggest risks are single points of failure, such as the primary database going down, which could prevent users from viewing their schedules. To improve availability for reads, we introduce a read replica. Calendar views are read-heavy, so the calendar read service can query the replica. This allows users to continue viewing their calendars even if the primary database is temporarily unhealthy. And lastly, we want to enhance the system to be performant, which means calendar views must load instantly, edits return quickly, and reminders fire on time, even during traffic spikes. The main risks are overwhelming the database with repeated read traffic and slowing down writes by doing too much work synchronously. To protect read performance, we place a cache in front of the calendar read service. Common views like today or this week are served directly from cache, reducing database load and improving response time. For time's sake, I've walked through only one example to show you how I'd enhance the key workflows to reflect the non-functional requirements. But in an interview, you should explore multiple design decisions to thoroughly enhance the workflows you selected to reflect the non-functional requirements. Now that we walked through the deep dive, it's important to remember that every architectural decision comes with trade-offs. Let's briefly examine what we're prioritizing and the trade-offs we're making and why those choices make sense for the product. One key trade-off is performance versus simplicity. We added caching so calendar views load instantly since users check their schedules frequently. The trade-off is added operational complexity because we must maintain and refresh the cache whenever events change to ensure users don't see outdated data. We accept that complexity because in a time-sensitive product like Google Calendar, speed and responsiveness are critical to the user's experience. Another trade-off we made earlier was making the notification service asynchronous. When a user creates or updates an event, we return confirmation immediately and process invites and reminders in the background. The trade-off is that users might experience a slight delay before attendees receive an invite, and in rare cases could postpone notifications. We accept this trade-off because we don't want to block users from saving events while notifications are processed. Ensuring the event is confirmed immediately is much more important than delivering invites at that exact same moment. And that's it for this video. I hope it was helpful in showing you how to answer system design questions for product managers. In my next video, I'll cover all the technical concepts you need to know for system design interviews and show you how you can apply it to your answers as well. Thank you so much for watching, and I'll see you in the next one.